Welcome. Now we are going to make some discussion on maximum likelihood estimator. Consider a population with probability distribution which is given by f of x comma theta. Okay. Elements in the population are realizations of the random variable x which has the density function f of x comma 0 or a mass function f of x comma 0. And here this theta is an unknown parameter, that is what we are trying to estimate. So for which we take a random sample from the population, and the likelihood function of the random sample is defined by L of theta, which is the product of individual densities of each variable. Okay. In maximum likelihood estimation technique, we try to find out this theta such that this L of theta is attaining its maximum value. Okay. When we consider this, when we try to find out the maximum value, what do we do? Anyway, now that this x1, x2, xn, these are all some known quantities because we have taken the sample, so these values are known from the sample itself, whereas this theta is unknown. Now this L is a function of theta, and we try to find out the maximum value. In that case, what is going to happen? The derivative of this L with respect to theta should be 0. Okay. But in some cases, okay, not only in some cases, in many cases, we consider log of this L of theta and we find out the derivative of this one with respect to theta. Now, if you see here, it is given in terms of partial derivative. Why so? Because I have told you guys that this x1, the value of this x1, x2, all these things are known from the sample. But once we fix a sample, then these values are known. But for a moment, this entire stuff is now some function involving x1, x2, xn and theta. But we are interested only in theta. That is why we are going to find out either del n del L upon del theta should be equal to 0, or we just take the log and we find out del log L of theta upon del theta, equate this to 0. From this we go for this. Why do we take log? Because if we have these quantities, some complex type of quantities we have, taking logarithm will bring it to some simplified form. Okay. And remember, while taking the log, this is an increasing function. So this does not affect the original function. Whether you perform with L or log L, it is completely up to you. You are free to choose whether to use with L of theta or log L of theta. And when you put this quantity to be equal to 0, whether you are doing this one or this one, that doesn't matter, from which you will have some value for this theta. Okay, and that theta we are going to denote it by theta hat, and this is going to be the MLE for that theta. Okay. Now we have an example here. We have taken a random sample from the Poisson distribution with parameter lambda. Now we are asked to find out the MLE. Okay. So the Poisson distribution means the probability distribution is given by what? Is f of x comma lambda, and here it is e to the power minus lambda, lambda to the power x upon x factorial, where x can take any value from 0 onwards. Okay. Now let us write down the likelihood function. For what? Likelihood function of the sample. That is, here the unknown parameter is lambda. Okay. It is x1 comma lambda, product with x2 comma lambda till xn comma lambda, isn't it? So when you write it down, it is e to the power minus lambda, lambda to the power x1 upon x1 factorial, e to the power minus lambda, lambda to the power x2 upon x2 factorial. Like this, still we have e to the power minus lambda, lambda to the power xn upon xn factorial. Now we can simplify this as 1 upon x1 factor, x1 factorial, x2 factorial till xn factorial, and this e to the power minus lambda, so this accumulates as e to the power minus n lambda, and lambda to the power x1 plus x2 till xn, isn't it? Okay, if you see, your lambda is in the power as well as in the base. Now that we wish to differentiate this one with respect to lambda, in these cases if you take a logarithm, that would be helpful. Okay, so now let us consider log of this L of lambda. So log of the entire stuff, what happens? So whatever is in the numerator, it is the product of two terms, so it gets into two different logs. So log of e to the power minus n lambda plus log of lambda to the power x1 x2 till xn, and whatever is in the denominator, it is log of x1 factorial, x2 factorial till xn factorial. Okay, so now this becomes minus n lambda, simply minus n lambda, isn't it? And here we have the summation I runs from 1 to n xi, that is in the power, multiplied with lambda, multiplied with log lambda. Okay, and this is log of x1 factorial, x2 factorial through xn factorial. Now let us try to differentiate this one. That is, we are going to put the derivative of this one with respect to lambda. With respect to the unknown parameter, we need to differentiate and equate this to 0. So from minus n lambda, we get minus n. And from here, what do we get? We get summation I runs from 1 to n xi divided by lambda, isn't it? The summation is not affected by the differentiation, only this log lambda gets affected, that is 1 upon lambda, and this quantity is 0 since it does not have any lambda term. So from which what we get is this summation I runs from 1 to n xi upon lambda is simply n. So from which what we get is lambda is summation I runs from 1 to n xi upon n. So this is our maximum likelihood estimator for this lambda. Okay, and what is it? It is nothing but the sample mean, isn't it? Okay, so here the MLE is, so for this problem MLE is sample mean. Okay, moving to the next problem. Again here we have a random sample from an exponential distribution with mean beta. We need to obtain the MLE of this beta. Okay, so PDF is f of x comma beta, which is given as 1 upon beta e to the power minus x upon beta for any x positive. Okay, and likelihood for this beta is f of x1 comma beta product with f of x2 comma beta till what, f of xn comma beta, since we have a sample of size n, and this is 1 upon beta times of e to the power minus x1 upon beta, 1 upon beta times of e to the power minus x2 upon beta till 1 upon beta times of e to the power minus xn upon beta. So we have this beta for n times, so 1 upon beta to the power n and exponential of minus x1 upon beta plus sorry, again it is minus, right? So minus x2 upon beta till minus xn upon beta. So this can be written as exponential of minus summation I runs from 1 to n xi upon beta. Okay. Now let us take logarithm. Log of L of beta. So it is going to be log of exponential of that quantity. Okay. Let me write it explicitly. That is minus I runs from 1 to n xi divided by beta. Okay, minus log of beta to the power n. So this log and exponential gets cancelled, so we are left with minus summation I runs from 1 to n xi upon beta, and this is going to be minus n beta, isn't it? Sorry, so it is going to be minus n times of log beta. Okay, now let us differentiate this one with respect to beta. So log of L of beta. So from the first term, what do we get? We get summation I runs from 1 to n xi divided by beta square, right? And from the second term, we are going to have minus n upon beta, which is to be equated with 0. Okay, and we know this mean cannot be 0. So this further reduces to summation I runs from 1 to n xi upon beta minus n is 0. So from this we can very well deduce this beta hat is summation I runs from 1 to n xi upon n, which is again the sample mean. Here also our estimator, maximum likelihood estimator, is the sample mean. Okay, here what we have done is that we have taken this 1 upon beta as a common quantity and we brought this beta to the other side since it is not 0. Okay, this does not affect too much and we are able to calculate the other values, right? And moving further, we have next problem, that is a sample is taken from a normal population with mean 0 and variance sigma square. We need to obtain the MLE for the sigma square. Usually if we have mu also, then we need to find out mu and sigma square. Now that becomes a identification of two things. Just to make the things easy, we have mean 0 and variance sigma square. Okay, let us try to understand this one. So now that our PDF is f of x comma sigma square is unknown. Okay, so the general PDF, that is f of x, is what it is, 1 upon under root 2 pi multiplied with sigma exponential of minus half times of x minus mu upon sigma whole square. This is the PDF of a Poisson distribution. Now our mu value is 0. So it is going to be 1 upon under root 2 pi multiplied with sigma and exponential of minus x square upon 2 sigma square, isn't it? Okay, now we will write down the likelihood function for this sigma square. Remember, we are trying to find out the sigma square estimate of this sigma square. So it is x1 comma sigma square product till xn comma sigma square. So it would be 1 upon under root 2 pi times of sigma exponential of minus x1 square upon 2 sigma square till 1 upon under root 2 pi times of sigma exponential of minus x1 xn square upon 2 sigma square. Okay, so this can be written as, we are going to have this 1 upon under root 2 pi. This is for n times, isn't it? Okay, and sigma to the power n, because we have n times, and exponential of minus summation I runs from 1 to n xi square divided by 2 sigma square. This is what we have. Okay. Now we need to do some calculations over here. Let us take log of L sigma square. So when we take log that exponential term, so log of exponential of minus summation I runs from 1 to n xi square divided by 2 sigma square minus log of under root 2 pi to the power n minus log of sigma to the power n. Right? Okay. Now what happens here? It is simply minus I runs from 1 to n xi square upon 2 sigma square, and this is some constant quantity. Let that be there as it is. So it is n times of log of under root 2 pi minus n times of log sigma. Okay. Now we need to differentiate it with respect to what? With respect to sigma square. In previous two problems, we were just differentiating with respect to the respective variables, either beta or lambda. That was fine. Now we are going to differentiate with respect to sigma square. So if you can directly perform it, just do it. If not, what you can do is that you just let this sigma square to be some variable, some other variable. So what happens to your log of LU? Okay, this gets transformed as minus summation I runs from 1 to n xi square divided by 2u minus n times of log under root 2 pi minus n times of log of u to the power half. Right? So this can also be written as n upon 2 times of log u. Now you perform the differentiation. Okay, that is delta log L of u upon del u, because we need to differentiate with respect to sigma square. Okay, so in this case, what is going to happen? This is summation I runs from 1 to n xi square divided by 2u square. Okay, and this term, when we differentiate, it is 0 since it does not involve anything, and minus n upon 2u. This has to be equated to 0. Okay, so from which, again, this 1 upon 2u times of summation I runs from 1 to n xi square upon u minus n is 0. So from which your u, that is your sigma square, is summation I runs from 1 to n xi square, this entire thing divided by n. So it is your sigma cap square. This is the maximum likelihood estimation for this case. That's it. Thank you.